Hello, everyone. Welcome back. So today we'll learn about the derivatives of trigonometric functions, or just call them trig functions. So our goals will actually learn them, what they are, and also be able to use them. And also want to be able to use basically anytime we evolve a trig function, we also want to be able to use it if the trig functions evolve in other kinds of functions. So basically, if use the trig function with other derivative rules like the product rule or the quotient rule or with involving a constant or something like that. Also be able to take higher order derivatives. We want to be able to use trig derivatives in all those ways as well. So first, let's start by talking about the first one. So let's talk about the derivative of sine. And you go and see here, it says the derivative of sine of x is actually cosine of x. So let's go over here to the right and kind of understand why that makes sense, why that's true. This isn't a proof, it's kind of an intuitive way of thinking about it. So let's look at our axis. Of course, this is our x and y. And actually do this in terms of angles. Of course, here's 0. Here's, do this in radians, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, if you remember that for cosine, also for sine and cosine both, the period, these are periodic functions, they all are. And the period of sine is 2 pi. That's the length of the repeating part. Here it goes from -1 to 1 to -1. So it looks like this. You draw it. Actually, let me see, change the color here. So I'm going to make this a different color. Just differentiate it to make it easier to see. So remember the sine graph looks something like this. Once again, this is one, goes forever in both directions. That's basically one period of it. Now, let's also think about remembering that the derivative gives us the slope of the tangent line at a point of a function. Let's think about what's happening with the tangent line. So actually, I may change, try a different color for that. Ooh, let's try orange. Work. Okay. So first, I was thinking about this point right here. So let's pick out pi over 2. That's where sine has a maximum value. And if you notice right here, then our tangent line would actually be horizontal, be flat. Okay. That's also true at 3 pi over 2. Okay. Now, let's think about some other places, like, for example, the spot right here at pi, for example. Okay. It's obviously going downhill from left to right. So it says a negative slope. So our slope of our tangent line there would be negative, and that's kind of where it's the steepest, kind of shallows up. And like right here at 0 and at 2 pi, it's actually increasing. Okay, so right here and here, it's increasing. And these should be pi and 0 and 2 pi should be the same slope. It's a little harder to see that. So let's actually go down a minute, and then let's actually use this to help us draw what we think the derivative of our, get an idea what we think the derivative of our, here, what its derivative should be. So let's go back here. Let's go back to black for right now. So remember, this is y equals the sine of x. Now, basically, we'll use the same radian. So 0, pi over 2, we try and line them up. Pi, 3 pi over 2, and 2 pi. Okay, so this is going to be, in this case, be y equals the derivative of the sine of x. Okay, I think I'll change to, let's kind of just use purple again, that's fine. Something different anyway. Now, let's think about what should happen. Now, getting exactly the exact shape is a little harder. We kind of imagine that we pick up some important things by understanding the slope of the tangent line, these points we mentioned. Okay, so remember, um, the slope of the tangent line is the same as the derivative. Right here, the slope of our tangent line should be 0. So right here, at like pi over 2, and also at 3 pi over 2, our derivative should be 0. This is where the slope of the tangent line is 0. Okay, now, also, right here, we said basically at this point right here, this should basically be a maximum Actually, no. So here our slope should be, here our slope or tangent line is negative. And this is basically the maximum negative slope we have in terms of absolute value, the largest. So basically it's going to be negative, it's going to be below the x-axis. It should be down here somewhere. That's a maximum value. And then similarly here, these are our maximum positive slope here at 0 and 2 pi, so they should be up here. Now, once again, exactly where they would be is going to be as clear from this, what we're doing, but you'll get the idea. Okay, if you draw that then, it should look something like this. So this gives us an idea of how a function is derivative related is once again understanding that the derivative gives the slope of the tangent line. Of course, this is the graph of y equals cosine of x. Okay. Now that's of course once again not a proof that that is the derivative. That kind of gives you an idea of how they're related. Okay. So once again, wherever you're in your original function, wherever the slope of the tangent line is 0, that's where your derivative function will actually cross the x-axis. When your slope is negative, see the slope here of our original function is negative between pi over 2 and 3 pi over 2. It is here. Has a maximum value right here. Or well, in terms of steepest value here. So the lowest, most negative value right here. And the most positive values here at 0 and 2 pi. All right. So those are the derivatives. And so we could do a similar thing. We won't take the time, but also we could also find the derivative of cosine is actually negative sine. So if you took the graph of sine and flipped over the x-axis, that'd be the negative sine. Okay, we do a similar thing there. So let's take just a moment and practice with these two, and then we'll get to the others. Let's look at some examples. Let's go back to black. Okay, so number one, let's say we want to let's say we want to find the second derivative. We're going to call it one way to call it f prime double prime of x of, let's say, f of x is going to be, let's say it's cosine. Okay, so this we will practice with this and also practice with recalling what a higher order derivative is. So first, let's do the first derivative. Okay, so f prime, take the derivative of our function f, and according to this, so the derivative of cosine is negative sine. Okay, so that's the first derivative. Okay, then the second derivative, we just take the derivative of the first derivative. So it's a derivative of then of the first derivative or the second derivative of the original function. So remember how this works is basically this negative is like a constant, negative 1. This is being negative 1 times the derivative of cosine of x. That's a constant. We pass it through. So we have negative 1 times the derivative of cosine is negative sine of x. And then the derivative of that. And then simplify that. And then, of course, that's going to be positive sine of x. Okay, so that's f, the second derivative, f double prime of x. And, of course, you can actually take as many derivatives of these functions as you want. They don't go away like polynomials. All right, so that's the second derivative. And let's say, what if we wanted to do, then we want to say let's say it's called as part, is the same one, number 2. I might want to find f double prime of pi over 2 using the same function. Let's go back to our picture from above, and at pi over 2 for sine, actually, that y value is going to be 1. Okay, so we can find values like that. And also, let's see. If we wanted to find, let's say, find the equation of the tangent line at, how we find it at that point. So at pi over 2 and 1 of f of x. No, not f prime, just f of x. Okay, we use the same f of x. So we said that the derivative, or the derivative of the slope of the tangent line is our derivative. Okay, we want to find is what we want out of this. Y equals mx plus b. Okay, so our m, our slope, have to find the slope and also b, we'll do that in a moment, is going to be the derivative of x at pi over 2. Okay, so we just found a minute ago that f prime is, oh, wait a minute. No, never mind. Yeah, so cosine f prime, wait a minute, what happened? Okay, I apologize. I made some kind of stupid mistake here. Let me back up. I chose cosine, so derivative of that is negative sine. Actually, I think just this is wrong. I'm sorry about that. I wasn't paying attention to what I was doing. Yes, this should also be cosine. No, the derivative of that should be negative sine. Okay, sorry about that. So start with cosine. I was saying we start with sine. Derivative of that is negative sine. And take the derivative of that, we pass through the constant. So this then should be, the derivative of sine is going to be just positive cosine. And this is going to be negative cosine of x. Okay. Now, then the derivative of that will actually just be 0. Okay, because you take the derivative, crap, I said pi over 2. That's fine. Pi over 2. And at pi over 2, cosine is 0, so that's just going to be a negative 0 or simply just 0. Okay. Now let's actually change this. Let's do another f of x. This time let's do f of x equals the sine of x. Okay. So, right. So good. We're back on track. So this is a point on sine of x. Now, I want to find this. So we need to find f prime, and f prime of x is just cosine of x. And so that tells us then that f prime of pi over 2, of course, is cosine of pi over 2, which is 0. That's interesting. So our slope is 0 there. Okay. So m is equal to 0. So we have y equals 0x plus b. And of course, this term goes away. So our y is just equal to b. So remember, if you have an equation like that, y equals a constant, that's a horizontal line, which makes sense once again, our slope, our tangent line is 0. And so our b is just our y coordinate. Y is right here. Pi over 2 is 1. Okay. And so that tells us then that y is equal to 1. Okay. Let's actually take a minute and go to Desmos to make sure that's true. So go to Desmos. Let's hit the graphing calculator. And also it's mentioned, if you haven't used Desmos before for graphing sines and cosines. So actually, let me move my picture out of the way. Right here, we have on the wrench over here, you have the settings. Notice we can tweak between radians and degrees. Right now we're in radians. When we go to degrees, do that. Let's stay in radians. Just click on somewhere on the screen to get rid of that. Okay, so let's just do y equals the sine of x. Okay, that's a familiar graph. Let's enlarge it a bit. Of course, that's pi over 2. Let me actually slide it this way a bit. So pi over 2, pi 0, 3 pi over 2, and 2 pi. Okay, good. Now, if we do y equals 1, we want the tangent line at this point right here, and it should be a horizontal flat line. We said should be calculated y equals 1. And yeah, that's correct. That's the tangent line right there. Good. Okay. Now, let's move on. Let's talk about the other trig functions. Let's actually do something. We can actually improve some of these. So this should be number 4. Let's make this another example. Okay. Let's say I want to show that, let's do the derivative of tangent. So show that the derivative of tangent equals secant squared x. Okay. And also just remember when you see this notation, hope you remember this from algebra, what that means is this means we're squaring it just the way this was written, secant x squared. We're not taking the secant of x twice. We're taking secant of x and then squaring that number. Okay. Well, the way to do this is, or one way to do this, let's do it this way. So we're going to have the derivative of tangent x. Remember that tangent x is the same as sine of x over cosine of x. Okay. So what we're going to do then is we're going to use the quotient rule. Okay. So remember what the quotient rule was. So what we're going to do is we're going to call these, make this simple. We're going to call this top one f of x. We're going to say f of x is equal to the sine of x, and g of x is equal to the cosine of x. Okay. Then the derivative of each one of those, so f prime of x, we just said is cosine of x. And then g prime of x is equal to negative sine of x. Okay. Now, if you remember the quotient rule, the reason we picked that is the quotient rule looks like this. D with respect to x of, our numerator function is called f of x, our denominator is called g of x. And it looks like this. And this one's one where you have to memorize. So g of x times f prime of x. You have to memorize because it's minus or a minus. So you have to make sure you get the order right since it's a fraction. Then f of x times g prime of x over the denominator function g of x, and we're going to square that. Okay, so the other thing is here we now have all these values. Let's plug them in. And so the derivative of sine of x over the cosine of x. Okay, so g of x is the cosine of x. And then times f prime of x is also the cosine of x. All right. Then minus f of x, which is the sine of x. And then this is g prime of x, which is negative sine of x. And then this is all over cosine squared. Okay, remember once again, we write it down, squaring cosine itself, we write it like that. Okay, and so simplify. So here we have cosine of x times itself. That's cosine squared of x. Okay, this is going to be a plus since we have a minus and a minus here. And then sine of x times sine of x is sine squared x. And this is over cosine squared x. Okay, now, hopefully remember one of your identities from trig. This is one you may want to make sure you do remember. Cosine squared times sine squared. Let's write this over here. I'll say and cosine squared x plus sine squared x is equal to 1. What we have then is 1 over cosine squared x. And if you remember, then that is the same as, since 1 over cosine is secant, 1 over cosine squared is secant squared. And that's where that comes from. So that's why the derivative of tangent of x is secant squared x. Now, you can also do a very similar thing with cotangent. You'll find the same thing. So cotangent, right here, it says this derivative is negative cosecant squared x. Approach that the same way. What you do then is, remember, cotangent is reciprocal of tangent, so it's cosine over cosine. So you can do the exactly same thing right there. Okay. And it's also a practice with using the product rule, using actually the quotient rule with some of the trig functions. All right. Number 5, let's do another one. So number 5, let's say I want to show, let's do one of the other ones. Let's say I want to show that, how about do the derivative of cosecant? Show the derivative of cosecant, the d dx. In fact, I'm actually do something slightly different this time. Often in trig, if you remember, a lot of times use a variable theta. A lot of times use that with the radians. You don't have to, but everything works exactly the same. If I just replace my variable x with a variable theta, it's going to work the same way. So I'm going to say the derivative with respect to theta of cosecant of theta is just going to be negative cosecant theta times cotangent of theta. Okay. So we're going to do a similar thing. We're going to write cosecant. Remember, cosecant is 1 over sine. Right? This is 1 over sine. Okay. And once again, I'm going to use the quotient rule. Okay. And so here, this time, my function f of x is going to be the numerator, which is 1. And g of x is going to be sine of x. Or sine, sorry, sine of, crap, I'm used to thinking of x. So I'd make these thetas. So theta, theta, and sine of theta. Okay. Of course, remember the derivative of a constant is 0. So f prime of theta is 0. G prime of theta, and as we learned, is cosine of theta. So we're going to plug those in to our quotient rule. Okay, so let's look back up here. Remember quotient rule, what it said is that basically it was the denominator minus the derivative of the numerator first. And that's kind of one of the main things you have to remember to get this formula right. So the derivative with respect to theta of 1 over sine of theta is going to be the denominator function sine of theta times the derivative of f of x, which is going to be 0, minus f of x, which is going to be 1, or f of theta, times the derivative of the denominator function is going to be cosine of theta. And of course, that's going to be over sine of theta squared. Okay, now of course, this is times 0, that goes away. So what we have is negative cosine of theta over sine squared of theta. And of course, this is also correct, but I think there's a better way to write it. Now, remember what it says it should be is cosecant of theta times cotangent. Now, we have the negative up front, so let's see if we can get that. So this is some practice you probably did taking trigonometry, working with identities. So one thing we can do is remember that once again, sine squared, this just means sine times cosine, or sine times itself. So we have negative cosine on top, theta. It's the same as sine of theta times the sine of theta again. So 2 sine of theta is down here. And what I can do, remember, I can actually, this is a fraction. It's like the opposite of multiplying fractions. I can break this up. I can split this up into, have a negative up front, into cosine of theta over sine of theta times 1 over sine of theta. If you're unsure, just check it by multiplying across. Remember, with fractions, we multiply straight across. So cosine of theta times 1 is cosine theta, of course, a negative. Then sine of theta times sine of theta is right. We'll put those together, we get that. Okay. And then, of course, negative cosine over sine is negative cotangent of theta. And 1 over sine is cosecant of theta. And so the derivative with respect to theta of cosecant of theta is that. And that's why. That's actually is a proof. That actually is a proof of why that's true. It's using the derivatives of sine and cosine. And we can also do a very similar thing with secant. That's how you would practice do on your own. Is write the secant is 1 over cosine, go through essentially the same process and find the derivative of that. Okay. So now that we've seen some of the basics, and also use the product rule, let's use a few other ideas. So I think I'm up to number 6, I think. Number 6. All right. In fact, let me just make some general directions here. Let's say for these next few, we just want to find f prime of x. So I want to find the derivative of these. So let's also kind of incorporate some other rules. So number 1, let's say we had this. Let's say we have, let's call this f of x, e to the x times the tangent of x. Okay. Now, here we have 2 different functions multiplied together. Remember, that's tangent, it's not a plus, it's tangent of x. So what we'll use, remember here, is use the product rule. Okay. Remember, the nice thing about the product rule, it doesn't really matter which order we use since we're adding, unlike the quotient rule where the order does matter. So here, f prime of x. Okay. So I'll just start here. I'll just do the derivative of this one, where the derivative of e to the x is just e to the x itself. That's e to the x times the other function, which is just tangent of x, plus, now, derivative of tangent of x, let's look down here. It says that's secant squared. Okay. So the derivative of tangent of x is going to be secant squared of x times the other function, the first function, which is just e to the x. And that then is the derivative of this function, okay, using the product rule. Okay, number 2. And we have this. This is our f of x. So f of x is equal to 3 times the cosine of x over 1 minus cosine of x. Okay. Now, once again, obviously we have a quotient. Once again, let's use the quotient rule. What we're doing here, just practice incorporating the rules we just learned about trig functions into also being able to use the other rules we learned about differentiation. All right, use the quotient rule. So my f of x, oh crap, let's call this h of x. So I want to use f of x for these functions. So f of x is my top function. And so that's going to be 3 times the cosine of x. Then g of x is going to be my bottom function, 1 minus the cosine of x. Okay, so f prime. So remember, taking the derivative, we have a constant. Just pull the constant up front. The derivative essentially goes through it. So we have 3 outside. And the derivative of cosine, of course, is negative sine. And so the derivative of that then is negative 3 times the sine of x. And then here, g of x, g prime of x, the derivative of constant out front first is 0, minus the derivative of cosine is once again negative sine, and x, not theta. Okay, and so that's going to be just a positive sine of x, that derivative. Okay, so let's plug all this in. So h prime of x, let's go and do our denominator. So denominator is going to be our denominator here, squared. So 1 minus cosine of x squared. Let's leave that as it is. Rarely is a good reason to multiply that through. And then first, remember here is our g function. Okay, 1 minus cosine of x times the derivative of my numerator function, negative 3 times the sine of x. And then over here, we have a minus in between. And then we just do the opposite. So we have f of x, which is 3, our numerator, 3 times the cosine of x, then times the derivative of my denominator, which is just going to be the sine of x. Okay. And let's see. Yeah, let's go ahead and let's do a little more algebra. There might be some simplification we do on top. Right now, we're going to leave the denominator as it is and make that better. So probably no reason to multiply that through unless there appears to be. So 1 minus cosine of x squared. And then once you have to FOIL this, actually, no, I'm sorry, I don't have to FOIL it. That's not. So 1 times negative 3 sine of x is going to be negative 3 times the sine of x. And then negative cosine of x times this. Negative times negative is positive. And 3 times the cosine of x times the sine of x. Okay, so take a look at that, make sure that's right. And then still we have negative 3 cosine of x times the sine of x here. All right, actually we can cancel things out. So actually we can cancel these two things out. And what we're left with then is, wrap up right here, negative 3 times the sine of x over 1 minus cosine of x squared. And we'll just leave it like that. There could be some other trig, identity you can use, but that's good enough. So that's our derivative. Now, if you want to take a second derivative, do essentially the same thing again. Be probably a bit of a pain, a lot more writing, but you can do that. Okay. Let's do one more thing. So this is different than we want to do. So this one, I want to ask this question: for what values of x, what values of x does this function f of x is equal to um, x minus sine of x have a horizontal tangent line? Okay, so what values of x does this function have a horizontal tangent line? So first off, let's go to back to Desmos, or go to Desmos and graph this, kind of get an idea of what we should expect. All right, I should get rid of both of these. Our function was x minus sine of x. So y equals x minus sine of x. Now, if you notice, it's kind of an interesting function, and it kind of grows. And what's happening here is, because if we just had the y equals x, it's space, that would just be a straight line. In fact, let's show that. So we just did y equals x. That's just a straight line. Then adding minus sine of x gives it that kind of wavy approach. But still, since x is increasing, and remember, sine only goes between -1 and 1, this thing is going to be increasing over, continuing going up here forever and continuing going down forever. But if we think about a horizontal tangent line, for example, right about here, somewhere we should have, looks like a horizontal tangent line. Okay. And also right here, right? Like 0 places right here where it's basically flat, we should have a horizontal tangent line. Okay. Now, remember how that's connected to the derivative. The derivative, wherever your derivative is equal to 0, that's where you have a horizontal tangent line. Okay, so that's what we're going to use to actually find those values. Okay. So you have a horizontal tangent line where f prime of x is equal to 0, since the derivative gets the slope of the tangent line. Wherever derivative is 0, that's where your tangent line is equal to 0. So first, let's find f prime. Okay. And so x minus sine of x, we did something like this just a moment ago. So the derivative of x is, remember, just 1, minus the derivative of sine is cosine. So 1 minus cosine of x. Okay. Now what we need to do is we want to solve. So I want to see whether it's equal to 0. So solve 1 minus cosine of x is equal to 0. Okay. And so this is a trigonometric equation. So first get the cosine part by itself, subtract 1 from both sides. And so we have negative cosine of x is equal to -1. And we'll divide through by -1, and we have cosine of x is equal to 1. Okay. Now, remember, where is cosine equal to 1? So this might be good to actually go back and look at the graph. Let's do that. So let's actually turn this one off a moment, and I probably need to zoom in a bit. Let's just do cosine. So now let's just do y equals cosine of x. Okay. So where is cosine 1? It's 1 at 0. It's also, now here it's a -1, but here it's 0 at 2 pi. Let's zoom out again, 0 at 4 pi. Also over here, it's 1 at -2 pi. So basically, it's going to be 0 at multiples of 2 pi. Okay. That's where we go. I mean, so sorry, where cosine is equal to 1, basic 0, 2 pi, 4 pi, 6 pi, and so forth. Also -2 pi, -4 pi, and so forth. Okay. So x equals, if we think about, it's going to be like, let's kind of do this dot, dot, dot. So -4 pi, -2 pi, 0, 2 pi, 4 pi. Remember, the dot, dot, dot just means this continues forever. So Out this way, it goes 6 pi, 8 pi, 10 pi, and over here, negative 6 pi, and so forth. Now, is there a better way to write that? And actually, there is. A better way to write that is that if you notice, what these all have in common are factors of 2 pi. So what we can say is x equals 2 pi times k. Or to use other letters, we'll use letter k. Okay. So we'll write this in a more compact way. And this is something you've also probably learned when solving trigonometric equations. So what can we call k? Okay. Where k is what does k need to be? Okay. So let's think about possible. So k could be just like a whole number. Would that work? Well, not entirely. You have to include both negative and positive values. K needs to incorporate those. But basically, want to make sure k can be essentially all the numbers like -4, -2, 0, 2, and 4. Okay. So basically, if you notice, all those have to be even. Okay. And also have to include negatives and positives. I just write this way. So k has got to be, for example, -4. I'm just going to use the dots, dot, dot, dot. -4, -2, 0, 2, and 4. Actually, wait. Well, actually, the way I wrote this, it's actually rid of the 2. Okay. A couple ways you can actually do this. Often there's more than one way to do this. So what I can say then is k is an even integer. Remember, it's integer, so we don't want any fractions. So even integer. Okay. Or we could say, we also write this x is equal to 2 pi k, which I started to write it. And this time, k would just be an integer. Okay. Now let's make sure that works. Okay. So this way, the k is an even integer. So if k is -4, that's true, but -4 pi, it's negative true, -2 pi. And also make sure you get 0. If k is 0, x is 0. That's true. Okay. Now this way, what if k is just an integer? All right. So if k is, do 0 first. If k is 0, makes that 0. Make sure you get these. K is 1. 1 times 2 pi is that. K is 2. 2 times 2 pi is 4 pi. Good. K is -1. We have gives us -2 pi. If it's -2, gives us -4 pi. That works. So basically, that's our answer to that equation. Remember, once again, our overall question was what values of x does f of x equals negative sine of x have a horizontal tangent line? So the horizontal tangent line are going to be whenever x is equal to 2 pi times k. Okay. Now let's go back to our graph and make sure this appears to be true. All right. So let's go back to Desmos. It is right here. Okay. Let's turn this off and turn this on. Zoom out a bit again. Okay. Let's look at a couple of these. Of course, 0, that's true. All right. Well, what if we do 2 pi? So 2, and also with Desmos, a nice thing, you just type in the letters pi, gives you pi, about 6.23. Is that true? Okay, hang on. There we go. We're back. Okay. Is that true right here? So about 6.2. I should need to zoom it out a bit. Okay, we see where it's about flat right there. About 6.28. That looks about right. Okay. What about -2 pi? Should be about -6.28. Yeah, that looks about right. Let's do one or two more. What about -4 pi? That should be right up here. So 4 pi is going to be 4 times pi, about 12.56. Yep, that looks about right. And then down here, the next one, -12.56. Yeah, okay, good. So the answer is that question. So basically, once again, we know where the tangent line is going to be. The tangent line would have a horizontal slope, because basically that's going to be where the first derivative is equal to 0. That's what we found. Okay, so let's quickly review what we learned today. What we learned then is basically the trig derivatives and what they are, and also kind of how to use them. So how to practice with them and learn not only what they are, and particularly kind of how some of these can be proven, but also how to also incorporate these derivatives, these trig derivatives into other functions. We're using the product rule, quotient rule, working with constants, and also working with using the derivative as the slope of the tangent line. Thank you. Have a good day.